Welcome back to ROBT308 Industrial Automation, Lecture 10, Program Control Instructions. Today's topics are as follows: Master Control Reset Instruction, Jump and Label Instruction, Subroutines, Immediate Input and Output, Forcing Capability of PLC, Safety Considerations, Selectable, Limited Interrupt and Fault Routine, Temporary End Instruction. YouTube videos on Program Control Instruction in Codices. Please watch these extra videos to learn how to use different control instructions in Codices. Program Control Instructions. We have these type of instructions: Master Control Reset, MCR, Jump and Label, GMP and LBL, Subroutine Functions, JSR and SPR and RET, Immediate Input and Output, IAN, IoT, IAM and IOM, Forcing External Input and Output, Selectable Time Interrupts, STI, STE, STD, Temporary End, TND, and Suspend, SUS. Master Control Reset Instruction. Program control instructions are used to enable or disable a block of logic control, or to move execution of a program from one place to another place. So here in SLC 500, so Program Control Menu tab for Allen Bradley SLC 500 PLC. Many of our examples on slides are from SLC 500, but as we had a menu for videos specifically based on the codices, you could refer to those videos for the codices specifically, but the concept is almost the same for Allen Bradley's and codices. So here you see that the program control, you have jump, label, JSR, RET, SPR, TND, MCR, SUC. We will explain these program controls in coming slide one by one. Hardwired master control relays are used in relay control circuitry to provide input-output power shutdown of an entire circuit. So these MCR relays, as we said, is designed to shut down the entire circuit. So here we have the MCR, and you see that how the MCR will disconnect all other relays or part of the program from the main lines. So, for example, if someone basically activate this master star, the MCR will be activated, and if someone stop this, then the MCR will be de-energized and the whole system shuts down. Okay, so it is basically a master key to turn on and off the whole system. It's good for the safety of the system. PLC manufacturers offer a form of a master control relay as part of their instruction set. MCR, master control reset, clears all set non-retentive output drawings between the paired MCR instructions. Okay, so non-retentive ones, yes. This is the important point here, that MCR doesn't touch the retentive values. Because the MCR instruction is programmed for safety reasons, it should not be used as a substitute for a hardwire master control relay, which provides emergency I/O power shutdown. Okay, so the MCR here, okay, it's instruction in the program, okay, for safety. But in the previous slide, we had an example of MCR relay, yes, and the MCR instruction should not be used as a substitution to a hardwired one, okay, and this is basically for having extra level of safety, one from inside the program and one from the outside of program. So MCR relay, which is hardwired, override the command of any other instruction, will shut off the whole system, and it doesn't care what's happening inside the program or PLC. If something goes wrong with the PLC, the program doesn't work, and the relay basically will override the whole commands of the PLC and will shut down the system. So this is the extra level of safety, and we should have both of them in place. So here we have a program, how they use the MCR instruction. So we have this on and off switch, and if we turn off the switch, okay, so if we switch it to the off position, the MCR shuts down the whole system, okay, and the whole system basically stops. So you see here, when MCR is de-energized, all non-retentive output de-energized. So the pilot light and the motor are non-retentive ones. And when MCR is de-energized, all retentive output remain in last state. Okay, so for example, the solenoid here, in this case, we assume that this is a retentive solenoid. Okay, so when the system shuts down, the solenoid will stay in the last position, in the last state. Okay, so it will stay in the last state. MCR fence zone with the zone true. So here we have, we are using MCR, we have MCR in place, but we have a start fence and we have an end fence. Okay, so it means that when the MCR is off, it only turns off the whole program between the start fence and the end fence. Okay, so whatever is in the zone will be shut off and will be basically eliminated from the rest of the program. Okay, but when it's on, this part of the program will be part of the whole main program. Okay, MCR fence zone with the zone false, and you have the start fence and the end fence here. Okay, the difference is that we don't have that active label at the top of the MCR. So this is opposite. The input A on this example now at this moment is false, and it's false. So the system basically will be true. If the input A becomes true, then the zone will become false. Okay, so this is the opposite of that. You see what is happening when the MCR is energized here in this case. So the output A is off. Okay, the output A is off, and the output B, because the output B is retentive, will stay in the last position. The last position is on and will stay on. Jump instruction. The jump instruction is used to jump over certain program instructions when certain conditions exist. The label instruction is used to identify the ladder rung that is the target destination but does not contribute to logic continuity. Okay, so we have a jump to the label. Jump operation program. Here we have one example. Here we have a jump and the label. When the jump is energized, okay, when the jump is energized, then instead of basically scanning a wrong tree, we'll jump to the label and we'll read the wrong 4. Okay, so basically we are skipping the wrong tree completely in the program, but the label itself doesn't contribute to the logic of this wrong. Okay, so it doesn't have any effect on the logic of this drawing, and basically it is just a label. Yes, it is not a contact or coil. Effect on instructions of jump drawings. So here, let's see what's happening. We have lots of inputs and outputs, and we have a jump and label here. Okay, and basically it jumps. When the jump is energized, it basically passes these 5, 6, and 7 drawings and goes and starts from 8. So here, jump program drawings are not scanned by the processor, input conditions are not examined, and the output remain in the last position. Okay, so these are the outputs between these basically rounds 5, 6, 7, solenoid 1, solenoid 2, and the pilot light 2. These basically outputs and the inputs inside, yes, so these limit switch also. So this limit switch won't be scanned, okay, so it doesn't care about the state of these ones from the input, plus it doesn't just update the state of them, okay, so they remain in the last state. Here we have a nice point here. Timers should be programmed outside the jump section, okay. We should always put these timers outside the jump section, because when it jumps, the timers, it will affect the performance of the timer, okay, and the timer doesn't work properly. Jump to label from 2 locations. It's possible to jump to 1 label from 2 positions. Here we could jump from here or here, okay, and it depends on the logic of the program. Yes, if it reaches to the first jump, it will skip the second one and goes to the label. If for any reason it couldn't reach this one, or for example, if this one is de-energized, the input A is de-energized, so or false, and the first jump is de-energized, so it doesn't jump. It continues reading other rounds, yes, and if the second jump is active and on or de-energized, then it will perform as it should and will jump to the label. Jump and labels in codesys. Again, please refer to the videos. Have lots of nice examples, but here you could see where is basically jump and the label and how you could use them. The concept again is same between different platforms. The only difference is the way the program is structured, and symbols. Sometimes symbols are slightly different from one platform to the other. Subroutine functions. A subroutine is a short program that is used by the main program to perform specific function. Okay, so it's quite similar to other type of programming system subroutines like C, C++, yes. JCR, jump, to subroutine. Okay, so jump to subroutine, jump to a designated subroutine instruction. Okay, it's basically to call that subroutine. Return from subroutine, exits current subroutine and returns to previous condition. Okay, so this is a return of that subroutine or function. Okay, so the subroutine identifies the subroutine program. So it's a label that shows this part is a subroutine. Okay, so here we have an example. When a subroutine is called from the main program, the program is able to escape from the main program and go to a program subroutine to perform certain functions and then return to the main program. So here we have a main program, and inside the main program, we have our jump to subroutine. If this wrong logic is true and the jump subroutine is energized, then it will jump to the subroutine. Okay, so the subroutine itself is labeled by SPR. Okay, so the program knows that this is a subroutine. This is a specific subroutine that we want to jump to, and at the end we have return. Once it reaches to the return, when the return is energized, it will back to the main program. Okay, so here we have, for example, jump to subroutine 3. Okay, so in Allen Bradley's, we have these U for the symbol of these subroutines and jumps to subroutine 3. Okay, this is a symbol. Subroutine, again, is a label and return. Flashing pilot light subroutine program. Anytime the weight on the conveyor, this is a conveyor, exceeds a preset value, the subroutine program scan and pilot light changes from on to flashing. Here we have a sensor that weighs the material on the conveyor, and when the weight goes beyond the limit or exceeds the preset value, then that subroutine for flashing should be activated. Okay, see the way they program it. Here we have our main program, and here we have a subroutine program. So for the subroutine, we are using SPR. So the software knows, the program knows that this is a subroutine. Yes, at the end we have a return. And here we have jump to subroutine. So when the sensor is activated, so this is basically the way they adjusted or tune the sensor. The tune is only activated when it reaches the preset value. Okay, so when the sensor is on, then it jumps to the subroutine, and we already had the annunciator program using 2 timers. It should be familiar to you, and it just do the flashing. Just do the flashing. Here, if the sensor is not activated, okay, the pilot light is just stays on, continuously stays on. Okay, because the T41 enable is false. This is for this on timer, and the sensor is basically false. So the negated value of the sensor will be true, and the pilot light will stay on. But once the subroutine is activated, so this T41 starts flashing, going from true to false, okay, with the period of 1 second, and the pilot light will flash. okay, until the sensor goes false or goes off, and again the pilot light will back to the solid state, will back to the solid state instead of flash. Okay, so here we have setting up a subroutine program. As we said, we are using a label SPR, and we should give it a name. For example, this is a subroutine tree, file tree, and finally we have a return. Inside the program, we should say jump to this subroutine file number 3. Again, basically implementation or instructions are slightly different between platforms. Check the videos for the codices. Passing subroutine parameters. So it's very similar, again, subroutines to functions in other programs like C. And if you want to pass some data or inputs to the subroutine, we should do it here in the jump to the subroutine instruction. For example, we want to pass this input parameter N730, and we want to return N750 to the main program. Okay, so this is the way we do it. The subroutine accepts N740 and returns 750. Nested subroutines are possible. Here we have one example. We are jumping, for example, from this main program to file 3 and return to the main program. Inside the first subroutine, we could have a nested one, jump to the file 4, and when it reaches to the return, it returns to this first subroutine. And again, another nested one. So we have basically 2 nested subroutines inside the first subroutine. Creating subroutines in codices or POUs. Okay, so this is the way they call it. So you see that in the add object, we could select POU. We could give it a name, POU, for example, 1 program. We could choose a type of the language, for example, ladder logic. Okay, and then press add. Now you see we have a main program and we have a subroutine program first, or POU1, the first subroutine. In basically under POUs, you could see subroutines, and then you could drag and drop it to the main program to use that subroutine. Okay, so once it's energized, then it will jump to the subroutine and will implement the subroutine. Okay, please watch other YouTube videos for further instructions. Immediate input and immediate output instructions. The immediate input and immediate output instructions interrupt the normal program scan to update the input and output image table files with current data. So IAN and IoT, immediate input and immediate output. So for the first one, IAN, immediate input, PLC5 instruction is used to read an input condition before the IO update is performed. Okay, so we had this scanning cycle. Yes, the first part of the scanning cycle, we read the last state of the inputs, then we'll move on to the execution of program and so on and so forth. Yeah, but if we use this immediate input, then the PLC reads the inputs and updates the input before the IO update is performed. Before reaching to the IO part of the scanning, we'll do another scan, okay? We'll do an immediate scan of inputs. And we use it when one input value is very important to us, yes, and or the speed of or frequency of update of that input is higher than the scanning frequency. So we want to basically double check. We want to be sure. We want to be sure what is the last state of the input. And then we'll use this specific instruction. Immediate output or IoT PLC instruction is used to update the status of an output device before the IO output is performed. So updating the outputs were the last state of scanning, but sometimes we want to update the out or a specific output or all outputs before reaching to that stage in scanning. Okay, so sometimes we are getting some fault signal or emergency, for example, shutdown signal, and we want to stop some safety sensitive coils and motors and outputs. So we want to basically update the outputs before reaching to that stage. Of course, the scanning cycle is fast enough, but for the sake of safety, sometimes we want to use this specific immediate output. So here we have an immediate input instruction operation. You see in the scanning cycle, the IO scan, program scan, and here, for example, inside the program, we use the IAN. So once this one is called or energized, then it will check the inputs again and return this specific input, for example, 12, input 12. So we'll do the scanning of the input 12 again, and we'll update the value of this input inside the program at this stage, at the middle of scanning, before reaching to the IO section. Immediate output instruction operation, again, inside the program, when it reaches to the IoT, for example, we want to update output 13. So we, based on the program, the last stage of the program, will update or send the value of this output to the output module, and will update the output, this specific output 13, and we'll back again to the program because we're at the middle of the program. We'll continue basically reading the program, and then at the end it will also update the outputs. Yes, so we'll do the normal scanning, but we have an interruption here. Forcing external IO addresses. Forcing allows the PLC user to turn an external input or output on or off from the keyboard of the programming device. Okay, so from the computer, we could override the real value of the input and output. For example, here, forcing is accomplished regardless of the actual state of the field device. Okay, so it doesn't matter what is the actual state of the field device. We will force that, we will change it. For example, here for I1 and O2, we want to force a value. Okay, so we want to force it, for example, to 1, and see how we could do that. You see that the force enabled. Forcing an input on. Here we have our input, and the input at this specific time or state is off. Okay, so normally I3 is 0. Okay, this is the actual state of input device and is 0. We want to ignore this value, override it with the value we wish, which is 1, from the terminal, from the uh, computer, from PC. And this is a programming terminal, forces the state of input I3 to 1. Okay, so here you see what happens inside the program. Normally, when the switch is off, I3 is false and the output should be off. But when we force it to on, it becomes on. Here we have forcing an output. This is basically a state of two outputs. Two of them are 0. Okay, so two of them have value of 0. Status of bit 025 remains at 0. And this is basically the actual value. Okay, this is the actual value for the 025. And we have 026. Okay, so what we want to do, we want to force 025 and we just don't want to touch 026. Okay, so the switch is off, 025 is false normally, but since we force it to on, now the switch or the solenoid here is on. And then this contact will be on. Okay, so this one is on, but the 026 value, this is the true value of the output, is false. Okay, is false and it remains false or off. You can enter and enable or disable forces while you are monitoring your file offline or in any processor mode while monitoring your file online. Okay, so either could be done either online or offline. But forcing, if used incorrectly, force function can cause injuries to persons working around the system and or equipment damage. So basically, the forcing is not, should be done very carefully. Is not a good practice to do the random forcing, so we should know the consequences. You must understand the potential effect that forcing giving input or output will have on machine operation in order to avoid possible personal injury and equipment damage. So we should be very careful when we do the forcing, specifically for complicated programs. If you force randomly one input, you don't know what would be the consequences, and sometimes better to avoid it in the online mode. Okay, so in the simulation is good. So usually they do the forcing in simulation. They do it in simulation because they want to check the performance of the program, but in online mode and on basically machine, it's better to be avoided. Safety circuitry. Sufficient emergency circuits must be provided to stop either partially or totally the operation of the controller or the control machine or process. These circuits should be hardwired outside the controller. So as we had previously in MCRs, yes, it's better to have a separate hardwire one, yes. So if we activate or engage the emergency button, it will shut down the whole system. and it doesn't care what's happening inside the program. So here you see that we have the safety wiring requirement here. It's a hardwire one. For example, if the fuse here trips, okay, so if the fuse here trips, we shut down the whole system. This is a master control relay MCR. Okay, this system will here basically will de-engage the whole system. The master control relay must be able to inhibit all machine motion by removing power to the machine I/O devices when the relay is de-energized. Okay. Safety PLCs are now available for applications that require more advanced safety functionalities. Both standard and safety PLCs have the ability to perform control functions, but a standard PLC was not initially designed to be fault tolerant and fail safe. Safety PLCs have redundant microprocessors or dual processors, so the extra one is used for backup. Safety PLCs have an internal output circuit associated with each input for the purpose of testing the input circuitry. Okay, so they have this specific system mechanism here inside designed to check the performance of inputs or testing or inputs. Safety PLCs use power supplies designed specifically for use in safety control systems and redundant backplane circuitry between the controller and I/O modules. So you see, they have redundant microprocessor and they have redundant backplane and power supply. All the stop buttons should be wired using a normally closed contact program to examine for an on condition. Usually, a normally open contact program to examine for an off condition will produce the same logic but is not considered to be as safe. Okay, so we are in safety considerations, yes, safety part, and you see that the stop buttons, yes, should be normally closed. Okay, should be normally closed. And when we engage them, when we press them, for example, it will close the circuit. Selectable timed interrupt. The selectable time interrupt STI instruction is used to interrupt the scan of the main program file automatically on a time basis to scan a specified subroutine file. Okay, so the difference here is that we have a time base here. The selectable time disabled instruction is generally paired with the selectable time enable instruction to create zones in which STI interrupts cannot occur. So here we have ST, okay, or ST enable or selectable time enable and STD, selectable time disable. And now we have a zone here. So see how we could use that. Selectable time disable instruction is generally paired with the selectable time enable instruction to create zones in which STI interrupts cannot occur. So here we have the zone, okay, STI execution will not occur between std and ste. So we cannot interrupt the program between these two. Fault routine. A fault subroutine file, if used, determines how the processor responds to a programming error. When the processor detects a major fault, it looks for a fault routine. If a fault routine exists, it is executed. If one doesn't exist, the processor shuts down. So we should have a routine, yes, for a fault. If that exists, okay, so then that will be scanned and will alarm, for example, the operator accordingly based on that, or try to fix, for example, the fault. Otherwise, the processor just shuts down the system. When there is a fault routine and the fault is recoverable, the fault routine is executed. If the fault is non-recoverable, the fault routine is scanned once and shuts down. Okay, so sometimes when there is a fault subroutine, that fault subroutine could recover the fault. Temporary end instruction. The temporary end, here we have TND, so we almost discussed these control instructions here. We are close to the end and we are now in the TND topic. So temporary end, TND instruction is used to progressively debug a program or conditionally omit the balance of your current program file or subroutine. When run conditions are true, this instruction stops the program scan, updates the I/O, and resumes scanning and drawing zero of the main program file. So basically, it's good for debugging. We could place it at the middle of the program. When it reaches to this instruction, it doesn't execute the rest of the program. We'll jump to the first of the program. So here we have one example. The TND instruction lets your program run only up to this instruction. So here, basically scans, and then reaches to the TND. Once we are here, it jumps to the beginning and doesn't continue performing or executing the rest of the program. So it's good to understand the performance of the first part, debugging the first part, and then move the TNT to other runs and check the performance of other runs as well. So you can move in progressively through your program as you debug each new section. You could move from one run to the other. You can program the TND instruction unconditionally, or you can condition its run according to your debugging needs. Okay, so it could have also some conditions. Suspend instruction. The suspend SUC instruction is used to trap and identify specific conditions during system troubleshooting and program debugging. So again, it's good for checking our program. So here we have a suspend and suspend ID. When the run is true, the SUS output instruction places the controller in the suspend mode, and the PLC immediately terminates scan cycling. Okay, so here the idea of the suspend, this is what the programmer chose. We could give it 120 or any other numbers, doesn't matter. So once it reaches to the SUS and the SUS is correct, or it's true, it suspends the program. Okay, or all ladder logic outputs are de-energized but other status files have the data present when the suspend instruction is executed. The SUS instruction writes the suspend ID number to S7 as it executes. Okay, so this is a file, this is basically a database. So if we look at the S file, we know that the S7 file, we know that, okay, this suspend is activated, not the other ones. We could have a couple of suspends. So why we use suspend and to know, for example, this is for the debugging to understand our program, to know, for example, that this contact is activated or that part of the program is executed properly, yes? And then we could look at the S7 file, see, okay, so the suspend number 100 is executed, not the other ones. You can include several SUC instructions in a program, each with a different suspend ID.